Okay, good morning. In the previous lecture, we visited the definition of information, and also we saw some of the sources of information, such as maybe the information, maybe an audio signal or a video signal, or it may be an image or some letters generated or some sentences in our daily talk. These are the different types of informations that are generated by different sources. And then we also understood the scenarios of information. For example, why do we use this information? Why do we need to care about the information? For example, maybe we need to, as engineers, we need to transmit the information from one place to another place, or we may need to process the information. For example, we use computer to process some data, right? So processing the information, and also sometimes we need to store the information. For example, we have an image or we have a video file that we want to store in a hard disk or any other memory devices. In that case, all the data what we deal with, or the information that we deal with, is the digital data. So if we can quantify the data, for example, there is a photo or there is a video, uh, or there is an audio signal, someone is speaking. In this case, we want to process that information, or we want to transmit the information. For example, if you consider the scenario of a mobile communication system where mobile phone is used to transmit the message from one place to another place. We call someone to transmit our voice from one location to a distant location. So in this case, it may be a transmission scenario, or maybe a processing scenario, or a storage scenario. All these cases, what happens is, all these, for example, when we transmit the message, so we transmit it through the channel, or when we process it, maybe we process it in a computer, or when we store it in some storage device. All of them have some constraints. For example, a storage device, maybe a hard disk or a disk storage, they have a capacity, maybe certain GBs or certain terabytes. Similarly, when we consider channel, it has certain limitations in terms of the bits that we can send, the channel capacity, or similarly, the processing ability of the computer. So, since there is a limitation on that, we cannot transmit or cannot process or store infinite amount of data. We need to have certain idea about what's the amount of information we can process it, or we can store or transmit. So in order to get that idea, we need to measure that information. This course will mainly deal with that. How initially we have some information, then how to measure it. Later on, how to transmit it, or how to store it, or how to process it, all this. So in order to do this, by considering the limitation of the process, underlying process, it may be a transmission or a storage, how can we represent the information in a better way so that we do not exceed the limitations of the storage device? However, we can do our task of storing the information effectively. So we need to have a trade-off. So that's what we deal with with that in this course, in the maybe in the second module and later on. Okay, at the end of the previous lecture, we also see that this message or information can be measured. So we got an intuition. So this intuition was from the Shannon's experiments. Okay, in the today's lecture, we will see how to measure the information. So here, some sources may emit the information such as letters, maybe teletypewriter, or some may emit some symbols, or in general, it may be an audio information, someone is speaking, or a video we can see around, and maybe it's a photo, or it's just the raw information, like someone is saying today's weather report. This is just a statement. There's also an information. So in this case, Generally, the information is generated at certain rates. How many messages are generated? For example, when I speak, how many sentences I speak per minute or per hour, and so on. And then we'll see based on this how to measure that information or how to quantify the information. But we are mainly interested in measuring the information in terms of bits because we are mainly dealing with the digital domain. Next, if there are two sources that emit different messages or informations, then how can we compare that? For example, if you want to compare the information generated by two or more sources, then we need to measure it, then we can compare it. So the fundamental task here is to measure or quantify the information. So we'll consider some examples that lead us towards measurement of information. So let us begin with the first example. The first statement or the first information here is this: sun rises in the east. The second statement or second information or message is this winter was dry and hot, unlike the previous ones. So if you notice here, the first uh, information is a very definite one. That is, every day sun rises in the east and there is no more argument. Everybody accepts it. But the second sentence, if you see, a winter was dry and hot. It is something strange, right? Winter should be cold, but he says, or this message says that it's dry and hot, unlike the previous one. That means there is a comparison with the previous winter. So this message can generate some questions or some discussions. Oh, winter is hot, but generally it should be cold, and so on. It is not a definite one, but the first sentence is a definite one. So from this, what we can conclude is the first one is a very common information, or the first information carries a common message. It's a common thing. Whereas second one is a debatable one, a questionable one. So the main observation here is an event that occurs certainly or very definite event such as sun rising in the east. It always happens. It carries less information. Whereas any other event that is not certain, like winter being hot, that will carry more information. So this is a general observation from this kind of messages. Always an information or a message that is very certain, that will always happen, that will carry less information, and an event that is not very certain will carry more information. So here the meaning is the definite event will have higher probability. That means it occurs with higher probability, higher chance, right? For example, sun rises in the east. Yes, it is very true. True means the probability is one, the highest one. Okay, so these two are the observations from the previous example. Now we will see some general cases. So by this, if we have Q messages, Q is a number, integer. For example, M1, message 2, message 3, and message Q, the last one. These messages can be some alphabets or maybe different statements. Maybe sun rises in the east, tomorrow is holiday, and so on. Or maybe tossing the coin or throwing the die, where we get different numbers when we throw it many times, and so on. So, okay, these are the different messages, informations. They occur with the probability of P1, P2, P3, PQ. That means P1 refers to the probability of occurrence of the first information or message, and similarly other things. Then the more probable message will carry less information. So among so many messages, whichever message is more probable, that means it will carry less information. So from this, can we have some idea about the information measurement? We will see in this slide. So here there is another general statement, that is sum of the probabilities of these events or these messages equal to 1. We generally know this. For example, if you toss a coin, there are two possibilities, either head or tail. If it is a fair coin, then there is equal probability. Either head will come or tail will come. Both have the equal chance. So we say the probability of occurrence of the head is zero point 0.5 and tail is also zero point 0.5. Total probability is 1. Similarly, this general example. So in this case, we can make the following observations. That is, information content of any message IMI is inversely proportional to its probability of occurrence. That is what we have seen so far. Based on this, what we can say, if the probability of occurrence is 1, that means a very definite event, then the information content of that message will be 0. Similarly, vice versa. And the third point is the probabilities varies from 0 to 1, and the information content of this particular message should be 0 or more than 0. That means it should be a positive quantity or non-negative quantity. So these three key observations we make here based on our example. And then you note here I'm introducing a term here that is called as self-information. So if there is any message M or MI, it occurs with the probability of PI, then the information content of this particular message IMI is called as the self-information of the message MI. That means that you have only one message MI and it occurs with the probability of PI. Then what do we measure? We measure the information content IMI. So that's the self-information of that particular message. This is a term we use. Okay, we have one more observation to make. Next, if there are independent events, then the total information content, for example, if there are two messages, then the total information content, we write it as I, is a sum of the information content in each message. For example, if there are two messages MI and MJ, then they occur at different probabilities. Then the total information contained in these two messages is nothing but, or it's almost equal to the product here, message 1, message 2, and also it's equal to the information content in this particular message plus the information content in the second message. So this is the total information content due to multiple messages. That's basically the sum of individual messages. So this is the fourth observation we make here. So based on this, what should we say? Content of any message is equal to the log of 1 by its probability or inverse probability. So in the first observation star, we mentioned that information content is inversely proportional to the probability of occurrence of that event. But here we are giving more meaning to that. I mean, Shannon gave this meaning, saying that information content, of course, it is inversely proportional to probability, but it is a logarithmic of 1 by probability. Why here there is log? Because of these four observations. If you see here, I of I multiply mj is equal to information content of mi plus information content of mj. Similarly, other observation 1, 2, 3, and 4. So he found that log is more meaningful to represent this inverse relation or to connect between these two terms. And also log has another property that log allows the quantity to expand. It grows slowly, right? You might have used the log scale as well as the linear scale. You know how the log variation is and how the linear variation is if you're plotting some values in a log scale or in a linear scale. Okay, here pi is the continuous probability. That means it varies from 0 to 1. So altogether, this is the key observation or key finding here from Shannon's uh, experiments. That is, information content of any message is equal to log of 1 by its probability. So here, when we say log, it can be base 2. So if it is base 2, then the unit is bits, so many bits of information. If it is base 10, then it is decit, and if it's a natural log e, then the unit is nat. But by default, we use log 2 in all our computations in this course. So the key equation here, our question was how to find the information content, how to measure the information, right? So we can measure the information, yes. The information content in the message is equal to IMI, that is equal to log of 1 by probability. Let us see, or let us try to understand this equation with the help of an example. So the given example here is, if the probability of certain event or certain message is 1 by 2, then its information content, how to measure? How to measure this message? So that's equal to log of 1 by pi. So here pi is 1 by 2. So that is log of 1 divided by 1 by 2. So it's basically log of 2, right? So here log refers to base 2 of 2. So it's basically 1 bit. Or you can uh, solve this stepwise, step by step. So basically log of 1 divided by 1 by 2. So log of a by b, that's equal to log of a minus log of b. So the same is applied here. Log of 1 minus log of half. So log of 1 is 0, you know. So it's minus of log of 1 minus log of 2. So that's equal to 1. So basically, we are applying this equation, exactly this equation here. Okay, so you please note that always we use log the base 2 because we want to represent the information in terms of bits. Okay, we will see another example, a little more complicated than the previous one. So here we have a source that emits 5 messages, one after the other. So the probability of occurrence of these 5 messages may be 1 by 2, 1 by 4, 1 by 8, 1 by 16, and also the fifth message has a probability of occurrence 1 by 16. Then how can we find the information content in each of these messages? That means we want to measure these informations. Maybe these 4 messages are nothing but 4 photos or maybe 4 videos. Their probability of occurrence is given. Then can we measure the information in each of these? Just apply this equation. Because we know the probability of the first message is 1 by 2. So log of 1 divided by 1 by 2, or it's minus log of 1 by 2. That's 1 bit. Similarly, information content in the second message is equal to log of 1 divided by 1 by 4, or minus log of 1 by 4. That is 2 bits. Similarly, in this case, it is log of 1 divided by 1 by 8. So that is 3 bits. Here it is 4 bits. And the information content of the fifth message is also 4 bits. Okay, so using the fundamental equation of measuring the information content of the message, we will move forward. How to find the average information content of a message? So in this case, we consider a sequence of messages. Earlier, we considered independent messages, I mean, individual messages. Maybe one message is generated. But here we consider that the source emits a sequence of messages at a time. For example, uh, my speech or somebody speaking many words at a time, many sentences at a time. In that case, how to represent the information content of the message, or a camera that gives out multiple photos at a time. okay, or you are throwing multiple dice at a time, so each one will have different outcomes, right? So that is the sequence of messages or a long sequence. Then how can we find out the information content in that message? That is the average information content. So here we actually consider two cases. One is the independent sequence, that is, when we have a sequence of messages, each message generated is totally independent of the other. The probability of occurrence of any event or any message is independent of the probability of occurrence of the previous messages or the next messages. For example, tossing the coin 2 times. First time you toss the coin, what do you get? You may get a head or a tail. Next time you want to toss the coin, what do you get? Again, you may get a head or tail, no problem. What was the answer or what was the outcome during the first event of tossing the coin, right? So these are independent events or independent sequences. Tossing the coin for the second time is not influenced by tossing the coin at the first time, right? They are totally independent. So this is called as a memoryless source. Second one is a dependent sequence. So in this case, the probability of occurrence of the current message or current event depends on the probability of occurrence of the previous one. For example, in English language, we have some words where each letter depends on the occurrence of the previous letter. We will see some examples in the later slides. Okay, I would like to give another example. So if you have watched the cricket game, assume that two balls left finally, and the team has to score 10 runs to win the game. Then, if the batsman during the first ball scores 6 runs, then is the match still alive? Is the team has a chance to win? Because one ball left, they need to score 4 runs. It is possible, right? Yes, the winning is still open. They can win the game. Okay, let us consider another scenario. The same, two balls left, and the team has to score 10 runs to win the game. In this context, if in the first ball the batsman scores 2 runs, then is it the winning still open? Generally, no, right? Under normal conditions, the team cannot win because the next delivery or next ball they need to score 8 runs. This is highly normally it's not possible. So the occurrence of winning the particular outcome is already decided by the first ball itself because they did not score well. Maybe just 2 runs in the first ball. As a result, the winning is already decided now. They cannot win, even though there is one more ball to play. So this kind of messages are called as dependent sequences or Markov sources. The source that emits such kind of messages is called as a Markov source because the second outcome is already decided by the first outcome. Okay, we will see these two cases in this module. How to measure the information content if the message is generated by an independent source, because in this case every message is independent. Second one is a dependent source or dependent sequence. In that case, how to measure the information content, because the subsequent messages are decided by the previous message itself. Okay, now we'll see the average information content in case of an independent sequence, independent long sequence. So consider that a source that generates n symbols. or n messages, maybe m1, m2, m3, up to mn. N is an integer, maybe 5 or 7, and so on, 6. Okay, each with a probability of p1 or p2, or in general pi. A message mi has a probability of pi. Now, here m1 will occur how many times? P1 times n. Similarly, any message mi will occur pi times n, right? Because this is not, these messages are not individual ones. This is a series of messages, many sentences, many photos, or many uh, voice messages. So if this message appears P1 times with the probability of P1, then in the total message here, what's the contribution of this particular message? P1 times n, right? If n is the total size of the message. So let us see to understand this with the help of an example how to understand this. For example, the sequence of message what we considered here may be A, B, C, D, E. These may be just alphabets or maybe 5 different images or videos and so on. So what's the total size of this message? Sequence of message, that is n is equal to 5, right? There are 5 alphabets. So in this sequence of messages, an independent message A occurs how many times? A occurs 2 times. So in this whole sequence of messages, A appears twice, right? So it's, what is the weightage of A in these whole messages? That is 2 times here. 2 by 5. Out of 5, 2 are A's. So this is the total weightage of A in this long sequence of messages. And B appears how many times? B appears just once out of these 5 messages, right? So that's a weightage here. That's what the meaning here. If the message is M1, its probability of occurrence is P1, then the total weightage of this message in a long sequence n is P1 times n. Okay, now with this knowledge, we'll try to determine an equation or a relation to find out the average information content. Since the information content of the ith message that we have already seen, information content of any message I is log of 1 by pi. So when you consider a long message of size n, then its contribution of that particular message mi is its probability into total length of the message and its information content. Information content is log of 1 by pi multiplied by its weight. If it was a single message, then this whole term is 1. Since it is not a single message, it's a long sequence having a length of n. So this becomes the total contribution or total weightage of this message. Okay, so total contribution of this message is pin log of 1 by pi, so many bits. This applies to all the messages in this sequence. So how to find out the total information content? We denote it as I total. I total is the total information content of this long sequence. So that is nothing but the contribution of each message in that long sequence. P1n log of 1 by P1, P2n log of 1 by P2, similarly P3 and so on until the last message. So now we use the word entropy. Entropy is nothing but the average information. So entropy is denoted by H of n. Entropy is denoted by H. So we need to find the entropy for a long sequence n. So that is equal to the total information content of that message divided by the length of the message. So many bits per symbol. Or you can also write it in another way as h of n is equal to pi log of 1 by pi for all those messages, all those so many n number of messages. So you may wonder here, where is that n, right? Because here, notice that entropy is given by the equation I total divided by n. So what is I total? We have already calculated. I total is equal to this plus and till the last message divided by n. So here this term divided by n. So in the denominator you have n. In the numerator also we have n as a common term. So n's will cancel. So we are left with pi log pi log pi and so on. So that's what we have written here. H of n is equal to the summation for all the terms pi log pi. So notice here that entropy is represented as bits per symbol. So that is how we find out the entropy of a message. So now we will understand this more clearly with the help of an example. So here we consider an independent source. I mentioned what is an independent source, and now it emits three symbols. For example, it emits A, B, and C with the probability of 1 by 2, 1 by 4, and 1 by 4. In this context, find the entropy. How do we find the entropy? So the solution is here. We know already what's the equation to find the entropy of an independent source. Entropy is given by pi log 1 by pi. So here the probability of the first message is 1 by 2 log of 1 divided by 1 by 2. Second message and the third message. So the total is this many bits per symbol. All right, so this is the second point in this module we have studied, how to measure the entropy. So you should be knowing this equation to find the entropy. All right, so we will move to the next concept, that is information rate. So information rate is represented as R. So that is nothing but the product of entropy and the number of symbols emitted by the source every second. A source may emit 10 messages every second or 20 messages every second. A camera may generate 10 photos every second, a burst of photos. Or a person may speak 10 sentences in 1 second. So all these are the rate of information. So multiplied by entropy gives the information rate. So information rate is represented as bits per second. So in the previous example, we considered that the source generates 1 symbol per second. So here we'll try to understand this with the help of an example. So here we are considering a discrete source. Discrete source means an independent source that emits different symbols one after the other. Discrete is not continuous, discrete. So an independent source also can generate discrete symbols. For example, the best example is the alphabets, generation of alphabets. They are discrete. Okay. So a discrete source emits 5 symbols each millisecond with a probability of 1 by 2, 1 by 4, 1 by 8, 1 by 16, and 1 by 16. You may notice that here the sum of probabilities is equal to 1. Okay. So now, anyway, we just need the probabilities. The probabilities are given here. Find the entropy of the source and the information rate. So I guess that from our previous discussions so far, we have all the information ready to find the entropy. We know how to find the entropy. It's nothing but pi log pi for all the messages. And information rate, the equation is right in front of you. Okay, the given data is there's a different probabilities. With the help of these probabilities, we'll try to find out the entropy. So entropy has to be computed like the information content or the weighted information content of every message. So pi log 1 by pi for the second message, third message, fourth and fifth messages. So how many bits per symbol we get? That is 1.87 bits per symbol. That's the unit of entropy. Next, we need to find the information rate. So information rate is nothing but entropy. We already calculated, multiplied by number of symbols emitted per second. So in the question, something, is there any hint? It says the source emits 5 symbols each millisecond. So the equation says what? Number of symbols emitted per second. What is given here? It's millisecond. So 5 symbols generated in every millisecond. So per second, how many symbols? Maybe 5,000 multiplied by the entropy. That is nothing but the information rate. Information rate is represented as bits per second. So if you compute this, you'll get the answer. So many bits per second. So that is regarding the information rate. So this is the third point we studied in the today's lecture. Okay, let us move on to a quick homework. So I would like to know your opinion in this case. For example, consider a binary memoryless source. A binary means this source emits either 0 or 1, maybe like tossing the coin. You have true or false, head or tail, and so on. Only two possibilities. It's a memoryless source. Memoryless source in the sense it's an independent source. All the outcomes have the equal probability. Then, when will the entropy attain the maximum value? So we need to find out when the entropy will be maximum. So what's the maximum entropy, and for what value you get the maximum entropy? So if we have only this much details, then how can we find the uh, instances when the entropy can be maximum? We need to have some example. For example, tossing the coin. Maybe I'll give some hint here. For example, P, we use a term P here to represent the probability of an event. X of k is an event, its probability of occurrence. For example, since it's a binary memoryless source, let us consider 1 and 0 are the two events. If the event value is 1, then its probability of occurrence is P. If the event value is 0, then its probability is Q, which is also equal to 1 minus P, because we know the total probability is 1, and there are only two possibilities, either 1 or 0, head or tail, true or false. So if P, the first event occurs with the probability of P, the second event must occur with the probability. The second event will have the probability of occurrence of 1 minus P. So now we need to find out, using the idea of entropy, for what values of P and Q the entropy will be maximum. So we know the equation for entropy, H is equal to P log 1 by P. Similarly, Q log 1 by Q. So what is the value of P and Q to have a maximum entropy value? So you need to think about this. Maybe P value is 0.2, then Q value is 0.8. Or if P value is 0.4, Q value is 0.6. Is the entropy maxima? I don't know. If you substitute, you can find out. But how many times you will substitute? It's a long calculation, right? So you need to think maybe in some other way. But the best way of solving this problem is you try to plot a graph. Maybe along the y-axis you have the entropy, on the x-axis you have the value of P or maybe Q, because if you know one, you know the other one. So you will get a graph as the P value varies, how the H value varies. You get a graph. So then you can conclude for what value of P the entropy is maximum. Then 1 minus P is the value of Q. Okay, so that's the end of today's lecture. We will see the rest of the things, especially how to compute the entropy or information content in case of a dependent or Markov source. Today we saw how to measure the entropy and information content as well as the information rate of an independent source. We will see the same for a dependent source.